Chapter 5 on nomenclature, which is the fancy word for naming compounds. And actually for drawing the formula of a compound from its name. Go both directions. All right, there are fairly simple rules that govern naming compounds, and they are agreed upon based upon the recommendations and the adoptions of the rules by this group. IUPAC. That stands for International Union of Pure and Applied Chemists. And what they say goes. Of course, they're not dictators. They get input from scientists, chemists in particular, all over the world, and then they make a decision that seems to fit the need best. All right. So the simplest compound for our naming purposes is a binary compound. That is, has two parts. Now, they say elements here. I don't think they mean elements from the periodic table. It can be periodic table elements, but it's more on the lines of two parts of the whole, two elements of the whole. And we're going to start off with just elements, of course, but we're going to graduate into, as a teaser, polyatomic components. So we start off with two elements, and they can be, and we're actually going to start off with ionic compounds. That is, where the two parts of them are ions. So you may guess that if one of them is an ion that's positive, then the other one has to be negative. That's the only choice you have. And in that case, we're talking about a metal, which is the positive ion, and a non-metal, which is the negative ion. And then we're going to move beyond that and use what we've learned in naming binary ionic compounds to name binary covalent compounds, in which you don't have ions. In fact, you can have, and usually do, in fact, I think I can say always, the binary covalent compounds will always have two nonmetals. So you know from your work with the periodic table now where the metals and where the nonmetals are in the periodic table. Most of the table is metals. We looked at that last week. No, last Tuesday, excuse me. So this is just a review. Here's an example of a nonmetal, chlorine, in this part of the table, and then sodium is a metal in this part of the table. When you put those two together, you have sodium and chlorine in a compound, and we call that sodium chloride. And the positive ions, if your ion is positive, it'll be called, this is review also, it'll be called a cation. And if your ion is negative, it'll be called an anion. So we can divide, for the purposes of naming compounds, and put some structure to the process so that it's easier to learn the rules and use the rules. We have three types of compounds. One, type 1. Is going to be metal, nonmetal. All right? Type 1 compounds. The defining feature of type 1 compounds is that this metal is only capable of having one possible type of charge. It can be a +1, +2, +3, whatever the case may be. It can have no other charge. That's it. When it's charged, that's its only choice. That defines a type 1 compound. So we might say single charge for the metal. Well, that's not a good word because single means one. Let's say just say one charge possible. How about that? So in the case of sodium, which is an alkali metal, and all of its group members can only have +1 charge. So that would include, actually above sodium is lithium, sodium, potassium, rubidium, cesium. Everybody in that group can only have +1 charge. That's it. No other choice. So we would write it this way. Okay? We know that halogens are a single negative charge, and sodium is a single positive charge. Right? If we put the charges in there just so that we can balance things, then we would say sodium +1, chlorine -1, you only need one each. So that's how you would write the compound. Now, how do you name it? All right, I'm going to come back to the type 2s and type 3s. Here we go. So when you name a compound, the first part of the name is the metal. And all you have to do is just say the name of the element. So this would be sodium. And the second part of the name, the anion part, we change the ending to IDE. So instead of chlorine, we say chloride. Okay. And that's typical for all but a few. For now, let's just say that's it. So here's chlorine, would be chloride. You can do the same thing with bromine, would be bromide. Or iodine would be iodide. Let's take another example. Suppose we're not in the alkali metals group. Say we're next door in the alkaline earths. All of those metals, when they charge, become charged with 2+ charge. So everybody in that group, beryllium, magnesium, calcium, strontium, and barium are all +2. So for instance, if we wanted to combine magnesium with chlorine, those are their charges. So now we would need 2 chlorines, like that. Right? And you wouldn't need the charges. When you write the compound, you don't have to put the charges in. I just do that for bookkeeping purposes. Now, how do we name it? Well, the metal comes first, and you just say what the metal is. And then the chlorine becomes chloride. Okay? Right, that's the distinguishing characteristic of the type 1 compounds is metal, non-metal, and the metal can only have one possible charge. This case it's +2. This case is +1. +3s. Right? We could say aluminum combined with fluorine, another halogen. Right? So aluminum is only 3 pluses. Fluorine is 1 minus. So we need 3 fluorines to balance the charge. 3 times -1 is -3, balances a +3. And this would be called aluminum fluoride. Okay? Now, to this point, we've taken the formulas, the compound formulas, and written the name. But you need to be able to go the other direction. Take the name and write the formula. So let's pick another one. How about, remember, the halogens are all -1, and the chalcogens, which is the oxygen group, are all -2. So in this case, let's take oxygen as the anion. And let's say we're going to make an oxide. All right, what do we want to do? What do we want to put? What metal do we want to put with that? Let's say, let's do aluminum again. So aluminum oxide, you need the symbol for aluminum, and you need the symbol for oxygen in there. Okay? In this order: metal, non-metal. Now, we know the charge on aluminum is 3 plus, and we know the charge on oxygen is 2 minus. Right? And how do you get that to balance? Right? An odd and an even. You can't just multiply, have a number of one of them and balance out the other. When you're faced with this situation, the best way is to use a math trick called cross multiplication. So I bring the 2 over here, bring the 3 over here. And then check yourself. Be sure it's right. 3 times 2 is 6 minus. 2 times 3 plus is 6 plus. It balances. Okay? So that's how we would write. Go. That would be aluminum oxide. Notice we don't have to say what the charge is on anything. The charges are fixed. That's type 1. Okay, you'll notice also that there's some other fixed charges in here. Let's see, zinc. Zincs, well, I can't show you the big periodic table, but I'll grab this little one. Zinc is right over here. It's a transition element, but it only has 1 charge, so it fits that group. Silver is like that also. Silver is a +1, zinc is a +2. Cadmium is a +2. Is it up there? They left cadmium off. So if there's only 1 possible charge, you use the type 1 convention for the metal. Let's see. Think just a second. How about one more? Let's write. Let me give you the name of a compound, and you write the formula. How about How about this one? Calcium nitride. All right. You look at your periodic table. You know that calcium is the second group over from the left, so that means it's a +2 charge. What do you do with nitride? Where did it come from? Nitride comes from nitrogen. Like that. Notice we don't say nitrogide. It just doesn't sound right. So nitride is the IDE ending for this one, and we only use the first part of the name. So nitride is sort of this convention, but it's modified to be a little easier on the ear. So what's the charge on nitrogen in this case? Well, nitrogen is one more toward the middle from oxygen. So the halogens are -1, the chalcogens are -2, the nitrogen group, the pnictogens, starts with a P. P-N-I-C-T-O-G-E-N. The pnictogens are -3. So this would be -3. Now, we're in a situation again where we have to cross multiply. So 2 comes over here, 3 comes over here, and we check ourselves. 2 times 3 is -6. 3 times 2 is +6. We're balanced. So that's the way you would write it. How about this one? I just thought of another one. Let's name this one. Calcium again, only we're going to combine it with carbon. Okay? So this is going to be Ca2C. Why? Because when carbon is an ion combined with a metal, it's a -4 charge. So we need 2 times +2 to be +4 to balance -4. Okay, now we need to name it. Right? Calcium. Carbide. Calcium carbide. Okay? Anybody who has say a grandparent or even a great-grandparent, if they're still living, who used to work in the mines, they know calcium carbide. Because calcium carbide used to be the source of fuel, gas, that would burn in their headlamps. They would have a little can up here, put some calcium carbide in it and add water. And the water would cause it to decompose into acetylene gas. Acetylene gas would be forced by the pressure inside up through this little hole, and you would light it. And it would form a flame right there with a reflector on it. And that's how you would see your way around in the mines, using calcium carbide. Of course, that could be a huge problem if you had lots of coal dust or you had collections of methane, pockets of methane. All you need is that ignition source, set it off. So that's why now we use electric lamps that are completely sealed and insulated so that they won't spark. That's what they use, calcium carbide. Okay, that's a type 1 compound. Now, let's see. These are just the rules that I gave you. They're in print, so you can read them. Let's see, more examples. You'll notice that the metals are always a fixed charge. Potassium is +1 charge, magnesium is +2 charge. Calcium is a +2 charge, but oxygen is a -2 charge, so you only need one of them, calcium oxide. Okay, Strontium is an alkaline earth, so it has a 2+ charge. Bromine is a halogen, it has a -1 charge. So you would say, and that's written correctly. You ought to be checking that too to be sure it's written correctly. Then strontium bromide will name this compound. And what we're looking for is not redundant. And let's see, I'm looking for the right word. Unambiguous. These two. In other words, what that means is that name goes with that formula and it can't go with anything else. It's unambiguous. You can't write any other compound from strontium bromide. You can't write any other compound from that name except this one. That's unambiguous. Ambiguity leads to confusion. If it's possible to write more than one compound from that name, then it's not unambiguous and would lead to confusion. Plus, we don't want redundancy. In other words, we don't want to have to say tricalcium dinitride. That would be redundant. We only need to say calcium nitride because this is the only compound that fits. That's it. No other possibilities. Okay, we should be ready for type 2 now. Yes, we're still binary ionic compounds. So let's make some space here. And type 2. Okay, we've still got metal, non-metal. Let's see, am I picking that up? Yep, okay. We've still got metal, non-metal, but now with a type 2 compound, the metal could have 2 or more different charges possible. Now, it won't have those multiple charges in the same compound. It just has 2 or more choices. Okay? So if there's multiple charge choices, then we use the type 2 convention. It's similar to type 1. Right? You name the metal, and then the non-metal is IDE, ending. But now, since the metal can have more than one possible charge, we have to specify in the name what that charge is. Okay? And we use a Roman numeral to do it. By and large, those metals that have possible multiple charges will come from the transition metals. They'll come from this central region right here. Except for those silver, zinc, and cadmium, because they only have one possible charge. But the rest of them, I'm pretty sure the rest of them are, let's see. Okay, there are 1 or 2 others, but I didn't have you memorize those, so you don't have to worry about them. All right, so here's an example. In order to write iron into a compound, we need to know what the charge is, right? Because where does iron come from? It comes from right here. right there, Fe. And it can have a 3 plus or a 2 plus charge. If it has a 3 plus charge, we say iron, Roman numeral 3. And then we follow it with the rest of the name. Now, fortunately for you guys, the convention now is you write the systematic name this way, right? When I was a student, we had to learn this older form. Iron 3 was called ferric, and iron 2 was called ferrous. The problem with that is, if we use the ic and us endings, when you go to a different element, the ic and the us mean something different. So it's not unambiguous. So IUPAC, in their wisdom, decided that we needed a better system, and that's what they came up with. Okay, so if we have, let's say we want to make a compound with iron and chlorine. Okay. I can't finish that until I know what the charge on iron is. I know what the charge on chlorine is, right? It's a -1. What's the charge on iron? Well, let's just start at the top. If this is a 3 plus, right, we need to write this with 3 chlorines to balance the 3 plus. And this would be named iron 3 chloride. Okay? Let's work it backwards from, well, I think we're going to have some examples. Let's not steal my own thunder. I will make a point here. Let's see, we've got these other examples. Now, tin and iron are not transition metals, but they do have multiple charges. Tin and iron come from part of the table. It's right over here underneath the nonmetals. Nonmetals over here, and then you got some metals down here. Tin and iron fit in that region, and they also have multiple charges possible. Mercury is a strange character. Mercury 2 plus combined with something else. Let's use chlorine again. Like that. That means this would be a 2, right? To make them balance. And this would be called Mercury 2 chloride. Okay. What would Mercury 1 chloride look like? Okay. The temptation is to say this. I just put 1 and 1. But mercury is funny. Mercury is, when it's single, it's always 2 plus. So this would have to be 2 plus. If it's 1 plus, then you need 2 of them. Okay. And now you would need 2 of those, because 2 pluses, 2 minuses balance. So this would be mercury 1 chloride, right? Fortunately, there are not that many like this. In fact, mercury is the only one I know that does that. So if mercury is a 1 plus, it's bound in a pair of mercury atoms. Okay, so let's look at some other examples. Let's see. Here we go. copper 1 bromide. Now, is that true? Is copper multiple possible charges? Well, you look at your periodic table, and you'll notice in your periodic table, let's see if I can get closer. In the upper right-hand corner of each of these boxes are charge numbers. And copper does have the possibility of a +1 or a +2 charge. So yes, that's the way you would write it. If for this formula, 1 copper and 1 bromine, copper must be a +1 charge. That's the only possibility, because -1 balances a +1, and they're 1 to 1. So that tells you that copper is copper Roman numeral 1 bromide. How about this one? Right? In this case, is that true? Well, look where sulfur comes from. Sulfur is in the chalcogen group. It's in with oxygen. Oxygen's a -2, sulfur's a -2. So yes, if this is a -2, we know that's a -2. This one has to be a +2. There's no other possibility. Not if it's written this way. So iron 2 sulfide would be the correct name for this compound. How about this one? PdO2. We know that oxygen, being a chalcogen, is a -2. So 2 times a -2 is a -4. So what will balance a -4 with only one of them? Lead must be +4. That's the only possibility. To balance charges, lead 4, Roman numeral 4, oxide is the name. How about this one? What is Cr? It's one of those that I had you memorize. Cr is chromium. So if we know the compound, if we assume the compound is written correctly, CrO2 means that oxygen being -2 times 2 is -4. -4 has to be balanced with a +4. And there's only one chromium. So the chromium, that one, has to be +4. It's the only possibility. So it would have to be chromium 4 oxide. Okay, let's make things more difficult. Why don't we? What's the correct name of the compound that results from the most stable ion for sulfur? Okay, so we got sulfur, and which is what? It's a chalcogen. So it has a 2- charge. And the metal that contains 24 electrons. So that metal has 24 electrons. Okay. Here's the trick to this problem. We have to make an assumption. If there are more than one of these, then that will influence what this is. So we have to assume there's only one. So if we assume there's only one of those, that means it has to be a 2+ charge, which means the number of protons has to be 26. Now that we know the number of protons, we can find the symbol for that element, which is 26 is iron. So we would write Fe(S). And the correct name for that would be iron 2 sulfide. Okay? We were forced forced to make that one assumption, that there's only one of them. Okay. Type 1s, type 2s. Both of them are metal, non-metal. Type 1, fixed metal charge. So when we name the metal, we don't have to say what the charge is. There's only one possibility. Type 2, the metal could have multiple charges, possible charges. So we have to say what charge we're using at the time for that compound. And we do that with the Roman numeral. Type 3 compounds. Type 3. Non-metal, non-metals. All right. Now, since we don't have a metal, non-metal, then we don't have ions. But we're going to use the binary ionic convention, naming convention, and work that into type 3 compounds. Right? So the natural question would be, at least in my mind, is if you have a non-metal and non-metal, which one comes first? Right? The general rule is the one that is closer to the metal side. So as a typical example, if you had, say, carbon and oxygen together, carbon is further to the left, which means it's closer to metals. So carbon would come first. And that's very often the case. There are exceptions, and you just have to memorize the exceptions. But in this case, if we had carbon and oxygen together, we would say carbon first. And then we would say oxide. But since they don't have a charge, there's no way for us to determine the formula from the name. Carbon oxide doesn't tell us enough information to say CO2. Because oxide might be a 2-, but what's carbon? We don't know. So for non-metals and non-metals, type 3 compounds, we say how many of each one are in the compound. And we use prefixes. Let's see, are they given to us? Here we go. These are the Greek prefixes for numbers. So mono would be 1, di would be 2. Here we go. Carbon dioxide. Notice, for the first member of the name and the compound, if there's only one of them, we don't say mono. Simply because it's redundant. If you have carbon there, you know that you've got at least one. So if we don't say 2, 3, 4, 5, 6 prefixes, then we know there's only one of them. Besides, it just doesn't sound right if we say monocarbon dioxide. Okay? However, if we write this compound, that 1 carbon, 1 oxygen, you do say you do use mono prefix for the second member. And we don't say monooxide. It just doesn't sound right. We drop one of the O's. Monoxide. Carbon monoxide, and everybody knows what carbon monoxide is. Right? It's an incomplete combustion compound from internal combustion engines. That's one source. And it's deadly. Right? It doesn't take much carbon dioxide to kill you. Okay, so the prefixes now are in this order. mono 1, di 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8. And I got two more. Nona for 9 and deca. Oops. For 10. So you need to know those prefixes. What do they mean? All right. We've already done that example, carbon dioxide. This will be sulfur. We don't say mono, it's just one sulfur. Sulfur, hexafluoride, hexa meaning 6. And notice in this case, the convention is followed. Sulfur is further to the left of fluorine, so sulfur occupies the metal position. It's not a metal, but it occupies the metal position in the name and in the compound in the formula. Here's one. Nitrogen and oxygen together. In this combination, 2 nitrogens, 4 oxygens. Dinitrogen tetroxide. So, in this respect, type 3 compounds are easier because you just say how many there are. How many atoms are in this molecule? 2 nitrogens and 4 oxygens. And you're done. How about this one? What is Se? Well, let's see. We have to look to see where Se is. Se is in the chalcogen group. Oxygen, sulfur, selenium. Right? So selenium is below oxygen, which puts it closer to that black jagged line which divides nonmetals and metals. So in that respect, selenium comes first. It's closer to the metals. So we write selenium dioxide. And we don't, if they're both nonmetals, then just put type 1, type 2 out of your head. If they're both nonmetals, they have to be type 3 compounds. And you use the rules for type 3. Right? So here's a flow chart that might help you decide what's what. Actually, this is useful. When you're faced with that choice, the first question you ask when you're going to name a compound. The first question is, what's the combination? Is it a metal, nonmetal, or a nonmetal, nonmetal? If it's a metal and nonmetal, then it's either a type 1 or a type 2. Okay. If it's a nonmetal, it's a type 3. And you just name it. If it's a metal, nonmetal, and you have to make a choice, what's the deciding factor? Possible charges on the metal. If it's a single possible charge, it's type 1. If it's multiple charges, it's type 2, and you use Roman numerals to say in the name what is the charge on the metal. Okay. Now, I mentioned earlier that binary compounds have 2 parts to them. In this case, we've got a binary ionic compound, but one or both of the positions, the positive, the cation, or the anion, is occupied by a polyatomic ion. What's a polyatomic ion? Well, work your way backwards. Polyatomic ion. It's an ion. It has a charge. it has atoms in it, but it has more than one type of atom. It has more than one element in its makeup. And it's formed in such a way that the entire unit acts like that ion. The charge is distributed over the whole unit of the combination of elements. So it behaves like a single ion. These polyatomic ions have special names. Some of them follow a logic that I'll try to point out as we go. But they have fixed charges. Now, the charge on a polyatomic ion is never assigned to any of the individual atoms. Let's see, we just had another one pop in. Melissa. Let's see, here we go. So that charge belongs to the whole group. I've got a list of polyatomics. In fact, in the review document, should be here, you not only have a periodic table, you also have a list of the polyatomics right here. Okay, so you can be assured that during the exam, whether you take it face-to-face or in the same folder in Brightspace where you find the online exam, you'll find useful information, and that polyatomic list will be included in that useful information. So be sure and have a copy of it before you start the exam, because then Lockdown Browser will lock you out and you won't have access to it. But I've got it up here on the screen too, I'll show you. This comes out of your textbook, and these are some of the polyatomic ions. But the complete list, well, I shouldn't say complete, a larger list of polyatomics is included in that useful information of the review document. And, well, I'll call your attention here. In that list that I just showed you, and in this list, there's only one polyatomic ion that has a positive charge, and that's ammonium. Notice that ammonium is the only name. In other words, when you put that polyatomic into a compound, you call it ammonium. That's it. You just call it ammonium. That's the name for this group, NH4 with a +1 charge. So if I put that in a group, NH4 with that +1 charge, and I combine it with something else, say an anion, a non-metal. Say I use chlorine, right? It's going to be NH4Cl, and that's called ammonium chloride. Okay, and you don't have to put the charges, right? They're just there for bookkeeping. That's the way you would write it. It's important that you recognize. You may not have to memorize all of them because I give you that list, but you do have to recognize when you have a polyatomic ion. You can't just say, separate these out and name it by saying nitrogen, hydrogen, chloride. That won't do, because that's a polyatomic ion, and there's the name. So that that extra credit document, 50 ways to name your compound. You have 50 examples in there. Some you name from the formula, and some you write the formula from the name. They're there to give you practice and a little extra credit too. Okay. So what if we went What if I did this? Magnesium, like that. Right? You should recognize this as a polyatomic ion, and this as a fixed charge metal. You look up there and you find that this has a -1 charge. Okay? So this whole group occupies the anion position, and this one, the cation position. So we would say, well, we wouldn't say anything yet because it's not balanced, right? 2 plus here, -1 there. So how do you balance? How do you write into a compound with a polyatomic to be sure that you're preserving the polyatomic part of that compound? If that's over the entire the polyatomic group, you need a parentheses, right? Because this acts as a single unit. So 2 times -2, -1 is -2, and then 2 plus balance the charge. And what type of compound is this? Type 1, type 2, type 3. Well, it's not type 3 because there's a metal. So it's either a 1 or a 2. Magnesium is a fixed charge. So it's a type 1. That means we would call it magnesium nitrate. And since these charges are fixed, that is unambiguous. That's all you need. This, you can use this to write that. And here's the nitrate. NO3 minus is the polyatomic ion. A lot of them only have 2 elements in them. Some of them have 3 elements. We don't have any here that have more than 3 elements in them. Some of them form logical groups. And what I mean by that is, if you follow a pattern that I'm going to show you, then you can memorize all 4 of those using this reason. Okay? Notice the endings here, the eights and ites, and the prefixes. Right? In this group, I always start with the 8, the chlorate. So ClO3 minus is the chlorate polyatomic. Okay? If I subtract an oxygen from chlorate, then I get ClO2 minus, and it's got the same charge on it. ClO2 minus. That's chlorite. Okay? If I subtract another oxygen, it's got the same charge, but it's missing an oxygen. So how do I name that? Well, there are no other suffixes that can be applied, so we use a prefix and a suffix. So we take this one and we prefix it by hypochlorite. Hypo is the prefix that means underneath. Right? That's hypodermic. Hypo, under the skin. So that's what the hypodermic needle, why it's called that, because they stick stuff under your skin with that needle. We can add one more, and the prefix for this one is per. Perchlorate. So it's got one more oxygen than this one does. They're all the same charge, but they differ in the number of oxygens. So if you know this pattern, you can start from here and say chlorate, chlorite, hypochlorite, perchlorate. And this is a halogen. You can substitute another halogen in here. Say bromine. If you substitute bromine in this one, we would call this bromate. Okay, you can do that for each one of these. Or iodine. You could say, substitute iodine in here. Now we would have hypoiodite. Okay? Now this is the oxides of halogens form the largest pattern group that I'm showing you here. There are others that have maybe 2 or 3 in them, like nitrite and nitrate, or sulfate. Take away an oxygen, you get sulfite. Or let's see. Some of the others, instead of the oxygens changing, the hydrogens change. So for this one, sulfate, we add a hydrogen and we get hydrogen sulfate. That is a polyatomic ion. It behaves as a single unit. Okay. So here's the full list that's in the review document and will be available for any exams. And it's divided down the center, but the left side is a duplicate of the right side. It's just organized differently. So on the left side, your polyatomics are sorted by names alphabetically. So acetated at the top, all the way down to thiocyanate at the bottom. On the right, they're sorted by formula. So alphabetical formula puts AS, or arsenic, arsenite, is first. So it depends on which one you're looking for and how you're looking for it as to whether you use the right side or the left side. So it's not twice as many. It's the same on both sides. It's just organized differently. All right. So those are your polyatomics. Here's a good example. This compound is composed of 2 polyatomics, NH4 and C2H3O2. And so NH4, we know, is ammonium. And C2H3O2 is acetate. That's it. They're fixed charges, both of them. So we can use a type 1 convention. We don't have to say anything about the charges. Ammonium acetate. All right, examples. All right, in this example, we have a metal and a polyatomic. OH minus. OH minus with a sodium plus balances. And we only need one of each. OH minus is hydroxide. That's a polyatomic ion. Here we have, I showed you this one earlier, magnesium nitrate, right? We have to use a parentheses because you can't split the group up. You can't change the subscripts of a polyatomic ion, right? 1 nitrogen, 3 oxygens, that's it. If you touch them, you die. So 2 nitrates gives you 2 minuses, And magnesium is a +2, so they balance. Ammonium sulfate. Right? There's another one with polyatomics in it. In this case, sulfate is a 2- charge, and ammonium is a 1+ charge. So we need 2 ammoniums to balance out the sulfate. Just use a parentheses. In this case, we've got a polyatomic in a type 2 compound, where the metal has a charge of 3+, because phosphate is 3-. Those charges, the polyatomics charges are fixed. So phosphate is a 3- charge. No other possibility. So if you only have 1 iron and 1 phosphate, then the iron has to be a 3+ charge. Iron, Roman numeral 3, phosphate. Okay, and there's a flowchart naming strategy. Let me see how I'm doing on time. We've only been at this for an hour. Okay, so I've been talking. Any questions so far? You're going to find that this stuff gets easier as you practice it. It might be hard at first. That's why I give you that review document with lots of problems in it to give you practice. And like I said before, one of your best friends in chemistry is boredom. If you get bored naming compounds, then you probably got them in pretty good hand. Okay. Okay, what's the name of this one? Do we have a polyatomic there? Now, clues. Look for clues. If you have a compound with 3 or more elements in it, and one of them is oxygen, it's not conclusive, but suspect polyatomic and go looking to see. So this one has 3 elements, one of them is oxygen. As it turns out, this is a polyatomic right here. We named it earlier, didn't we? This one's potassium. By the way, it's got a metal in it. Is this a type 1 or a type 2 compound? It has to be a type 1 because potassium is a fixed charge. It's an alkaline metal. And then this polyatomic is called chlorate. Okay? Potassium chlorate. And that's it. You don't have to say any more. We don't have to be redundant. This is unambiguous. Forgot to shut my phone off. Which of the compounds are named correctly in this table? Well, let's see. What type of compound is this one? P2O5. Right? We'll look for the elements. Where are they located in the periodic table? Both of these are nonmetals. So that means you use a type 3 convention. You just say how many of each one is in that compound. Diphosphorus pentoxide. That is correct. How about this one? ClO2. The temptation here is to look for polyatomics. But this is the compound. It's neutral. So we're not naming a polyatomic here. We're naming a nonmetal type 3 compound, which would be what? chlorine dioxide. That one's wrong. How about this one? Lead and iodine. Type 1 or type 2? Because it's a metal, it has to be 1 or 2. Right? Lead has possible 2 or more charges, so we have to use a type 2 convention. So we would say lead 4 iodide, 4 in Roman numerals. Lead 4 iodide. That one's wrong. Okay. How about this one? CuSO4. Do we have a polyatomic here? Yeah. We have 3 elements. One of them's oxygen. It's probably polyatomic. Look it up. Sure enough, SO4 is a polyatomic. Remember, all but one of the polyatomics in our list is an anion. So this SO4 should have a 2- charge. That means copper, if there's only one of them, copper has to be a 2+ charge. Copper 1 sulfate. Right? SO4 2- is sulfate ion. That's wrong. Copper needs a 2+ charge. So there's only one right one in this whole bunch. Right? It's just the first one is correct. The rest of them are wrong. All right. So now that we've gotten type 1, type 2, type 3 compounds and polyatomics covered, we were faced, or well, the chemical community was faced with legacy naming, to put it one way, legacy naming of acids. The alchemists of medieval Europe knew several what we call mineral acids. They knew hydrochloric acid. They knew nitric acid. They knew sulfuric acid. And they used them extensively in their researches, trying to convert stuff into other stuff. So we had to grandfather those in and try to form a logical structure from naming acids. Well, first of all, what is an acid? Well, an acid is going to start with hydrogen, at least 1, sometimes 2, sometimes 3. I think you can have 4, but I've never seen it. But you start with hydrogen, and then you have something beyond it. And very often, it's a polyatomic ion. Not always, but often. So that's how you recognize an acid. We always write it with a hydrogen first. Now, why do we put the hydrogen first? Because whenever we combine it with something else, this hydrogen dissociates from the molecule. And in aqueous solution, in water, that hydrogen goes into water, and that's what forms the acidic nature. Okay? So we put the one first that can dissociate. Now, if there are any other hydrogens in that molecule, and they're not here, then they're not considered what we call acidic hydrogens. They don't dissociate. A perfect example. C2H3O2. That is called acetic acid. And everybody knows acetic acid at 5% acid concentration, that's vinegar. But this is the only hydrogen that dissociates. These 3 hydrogens are locked in place. They cannot dissociate. So that's why we write them over here. We write this one there. So it's only got 1 acid hydrogen. Okay. Now that we know how to recognize an acid, Then we need rules for naming acids. Okay? The first rule is, don't look at the hydrogen. Look at the anion. Look at the other part of the molecule. Like that. Okay? And ask yourself, is there an oxygen? Is there an oxygen over here? No. If there's no oxygen, we always start the name with hydro. In honor of the hydrogen. And then I got a better approach. Hold on just a second. How would we name this compound if it were not considered an acid? In other words, HCl in its pure form is a gas. And we would name it hydrogen chloride. When does it become an acid? It only becomes an acid when it's dissolved in water. There we go. AQ, aqueous. Now that it's in water, the name changes. Now we call it hydro, and instead of chloride, we change the ending on the chloride to ic. And then finish it off with acid. So this would be the free molecule, hydrogen chloride, dissolved in water is hydrochloric acid. Because there's no oxygen there. We started with hydro. There's hydrochloric. How about this one? Here's a polyatomic. Right? But there's no oxygen. So we start the name with hydro. But what is this polyatomic called? Well, we look it up. Cn minus is the cyanide. Yeah, I think that's right. The cyanide ion. Let me see if I misspoke. No, that's right. This is the cyanide ion. So, if this were not dissolved in water, this is also a gas. This would be hydrogen cyanide. And it would be extremely hazardous to breathe this stuff. But if we dissolve it in water, now it becomes hydro cyanic acid. Okay? How about this one? Right? What would it be if it were not dissolved in water? It would be called, it's a gas, that's a coincidence, hydrogen sulfide. Okay? Now, hydrogen's a special case. It's not a metal. We treat it like a metal. And in this case, it would have a +1 charge. So 2 pluses means we need 2 of these pluses to balance sulfur, which is a -2 charge. So hydrogen sulfide is all you need. Type 1 convention. If we put it in water, now it becomes no oxygens, hydro. sulfuric. Right? So this is not a strict observance. It's not sulfic. We don't say, drop the IE in that, I see. We don't say hydrosulfic. Just doesn't sound right. So we expand it to sulfur and then add the ic. So hydrosulfuric is that acid. Okay, here's some others. Right? And they all start with hydro because there's no oxygen in that molecule. So you probably guessed that the next rule is for acids that do have oxygen in them. Okay. Now, if there is an oxygen in the anion part of the molecule, that automatically means that the acid is formed from a polyatomic ion. That's the only way you can get it in there, along with something else. Because if we put just hydrogen and oxygen together, we get a polyatomic hydroxide. So, well, except for water. Water is a special case. So we don't name water according to the acid convention. It's just called water. Okay, so if you do have an oxygen in the molecule, you don't say hydro. You do not start with hydro. Instead, you start with the anion part of the molecule. Example. So HNO3, we would normally say hydrogen nitrate. But to name it as an acid, we would take this part, and the 8 is converted to ic. Nitric acid. That's it. You just take this part, which is nitrate, and say 8 becomes ic. What if we had this one? HNO2. NO2 is not nitrate, it's nitrite. So nitrite is part of the molecule. Ites become us. So in this case, it would be nitrous acid. Okay? H2SO4. Notice that if this is positive and that's a -1, we're balanced. If we have this one, this is a 2- polyatomic ion, so that means we need 2 of these because it's a 1+. So we're still balancing charges. H2SO4 now, sulfate, ATE becomes IC. So we modify it just a little bit. Sulfuric acid is that one. Notice the difference between this one and this one. This one is hydrosulfuric. Okay. Simply because it has no oxygen. We started with hydro. This one has oxygen. We take this part of the molecule and 8 becomes ic. I mentioned this one earlier. C2H3O2- is the acetate polyatomic ion. So 8s become ics. Acetate becomes acetic acid because there's an oxygen there. So we start with this part of the name, Acetate becomes acetic acid. Now, it might seem strange, but this particular compound can be purchased 100% purity. It's called glacial acetic acid. The problem is it's not in aqueous solution anymore. I mean, it's 100%, but we still name it with the acid convention. So even though there's no water in 100%, we still call it acetic acid. Okay, here are your examples with ite. Ite becomes us. Ate becomes ick. Ite becomes us. And it's all based upon that polyatomic ion. Right? Chlorite. Remember, ClO3 is chlorate. So HClO3 would be chloric acid. And this one, HClO2, would be chlorous acid. How about this one? HClO. Right? Hypochlorite would be hypochlorous acid. And then if we go the other direction, ClO4, this is perchloric acid. Okay. This one is extremely hazardous. I used to use that in the laboratory to digest plant material, which is basically turning all the organic material into carbon dioxide and water, heating it, blowing it off, and what's left is the mineral content. It's very efficient at doing that, but you have to be careful. It's very reactive with the organic compounds. So if I put, if I have a beaker full of 70% perchloric acid, which is concentrated, and put that under the hood on a hot plate, and then I put a nice big chunk of butter in it, and then I crank the hot plate up to maximum, pull the shade, and evacuate the building, because it will blow a hole in that building. So how do we deal with it? Well, you do a pre-digestion. We use nitric acid. Which is safer, but not as effective. So we do a pre-soak, nitric acid in the plant material overnight, sitting on the fume hood, and then in the morning we come in and it's partially digested, and we add our perchloric acid to each one, turn up the heat, perfectly safe. All right. So here are comparisons. Nitric versus nitrous. Notice the difference in the oxygens. Sulfuric versus sulfurous. Phosphoric. You can also have H3PO3, which is phosphite. The phosphite would be phosphorus acid. And there's your acetic acid. And there's your decision tree if you want to use that. Okay, which one of these is incorrectly named? All right, so we're gathering everything that we've learned so far in this chapter and putting it to work to answer these questions. Is this one correct? K, NO3. K is potassium. NO3 is nitrate. Potassium nitrate. Type 1 convention, potassium is only one possible charge. That's true. We're looking for the ones that are wrong, right? So this one's good. This one's true. How about this one? Titanium and 2 oxygens, right? Titanium is possible multiple charge, so it's type 2 convention. We need a Roman numeral. Well, we have a Roman numeral. Is it the right one? Oxygen is a 2 minus charge, and there are 2 of them, so it's a 4 minus. So titanium needs to be a 4 plus. That one's wrong. How about this one? OH, hydroxide, is a polyatomic ion. And if you're given the formula, like this, and there's parentheses around it, that's a dead giveaway. That's a polyatomic ion. But there are 4 of them. Hydroxide is a -1 charge, so it's 4 minuses, and 10 has to be a 4 plus to balance them. 10,4 hydroxide is correct. PBr5, is that a type 1, type 2, or type 3? Phosphorus, bromine, they're both nonmetals. It's a type 3. So all you have to do is say phosphorus, pentabromide. Phosphorus, pentabromide. That one's correct. How about this one? That's an acid. It starts with a hydrogen, actually 2 hydrogens. And then it's connected to the polyatomic ion sulfite. Remember, ites become us's. And it's got oxygen in it, so we don't start with hydro. We just start with the name of the polyatomic ion. So sulfite becomes us, sulfurous acid. That's correct. So there's only one that's wrong. All right. So we're going to practice writing formulas from their names. Right? We know what sodium is, Na. Right? It's not SO, it's Na. It's Latin natrum is sodium. And then hydroxide is a polyatomic ion. In this case, you know it's polyatomic because what? There are no elements in the periodic table with that name. You've memorized all the others, and you know it's not among them. So it has to be a polyatomic. So we say sodium hydroxide, and we know hydroxide is a -1 charge for the whole, and this is a +1 charge. So that's, you only have to write one of each. Okay. How about potassium carbonate? Right? Potassium. What's carbonate? This is another giveaway. Besides the fact that there's no carbonate element in the periodic table, if you see ending in ATE, then you know there's oxygen in it. That's grandfathered in from alchemist days. ATE means oxygen's present. Well, ITE does too. But you look up your carbonate, and it's this one, right? +1 here. So we know that we need 2 of these. So K2CO3 should be the correct formula. Sulfuric acid. Right? With the name acid, you know it has to start with hydrogen. And you know it has oxygen in it, right? Because there's no hydro. So sulfuric, you work backwards. Ics come from what? They come from 8. So sulfate is the polyatomic. And then you look it up, and it's a 2 minus charge. So that means this one has to be 2 of those because it's a 1 minus charge. So H2SO4 is sulfuric acid. How about this one? Dinitrogen pentoxide. Well, look at the name. Nitrogen and oxygen, they're both nonmetals. That means we're looking at a type 3. second. They had a low battery warning. I forgot to plug in my battery. Okay, back to the topic. Dinitrogen pentoxide means that it just tells you how many there are. Dinitrogen pentoxide. You're done. That's it. Ooh, cobalt-free nitrate. We know cobalt. And we know nitrate. We know polyatomic ions have a fixed charge. This one is a -1. And we're given the charge on cobalt, 3+. So that means we need 3 of these minuses to balance that 1, 3+. There we go. All right. Okay, a little detective work here. Compound has the formula XCl3. XCl3. It's a good habit to get into when you have a word problem. Extract information from the word problem in a form that's not wordy. You don't want prose when you're trying to solve a problem. So I pull out information as I get to it. X could represent a metal or a non-metal. Oh, so this could be a metal or a metal or a non-metal. Okay, what could the name of this compound be? What could the name of this compound be? Well, it could be. Oh, I'm sorry. Multiple choice. There we go. All right. Now, we didn't have enough information. Now we have choices. All right. If it's a non-metal, then trichloride would be right. But the problem is, well, no, that's not necessarily a problem. It's definitely not monochloride. Right? Chloride could be. So by process of elimination, we know B can't be it. Because it's not one chloride, it's 3 of them. What are the possibilities? Well, could it be 10,4 chloride? If it was 10,4 chloride, then we'd have to have a 4 there, right? So we eliminate C also. How about this one? Phosphorus trichloride. That could be. That's possible. How about this one? Magnesium chloride. What would magnesium be? This is 2+, that's 1-, this would be 2. Right? So by process of elimination, that's the only one out of those choices, that's the only one it could be. Okay, last topic. Some compounds like to harbor within their crystal structure molecules of water. Now, the water in these compounds is bound in some way to the compound, but it's not part of the compound itself. These are called waters of hydration. And we have a special way to write them when we write the compounds. First thing you do is let's see, are we naming or writing? Okay, we're naming. So in this case, zinc sulfate, we're naming based upon our convention, right? Let's see, is zinc, yeah, zinc is a fixed charge, 2+. So we only have to say type 1 convention, zinc sulfate. So we say zinc zinc sulfate is this, right? But we know that zinc sulfate has 7 waters attached to this formula. So for every one of these, we have 7 waters in that crystal structure. Right? And we put these out separate because they're not part of the compound. And we put a dot there. Kind of like in math, when you write a dot means multiply. In this one, in chemistry, that dot in the middle of the line means attached to. These are attached to that. And we write that zinc sulfate heptahydrate. Hydrate refers to the water, and hepta refers to 7 of them. So that's the way you would write this compound. Zinc sulfate heptahydrate. Let's see, do I have other examples? No. Another example that you don't even know you have. You've had a compound with waters of hydration around you, unless you live in a really, really old house. But if you live in a house that was built, say, in the 50s or later, it's going to have this compound. Right? The short name for that is gypsum. So wallboard or gypsum board is in every house. But the chemical name for that, this is what they call a trivial name. But the systematic name is calcium. Calcium sulfate dihydrate. That's the proper name. Now, what happens to that water? Well, it stays there unless you do something. If you heat this compound up, say to 105, 115 degrees in that neighborhood, maybe even 125 Celsius, you can force that water to be removed. Right? So that would give you calcium sulfate, no waters. And that's the proper name, calcium sulfate, just this part of the name. But what we say about this in relation to that is, this is anhydrous, means it has no water in it. An is the prefix for not. When we're talking about atoms, atome means not cut. Well, in this case, we use an. An as a prefix means not. So there's not water, anhydrous. If you got any farmers in the family who use ammonia to nitrogen fertilize their crops, they need some special equipment to do it. But the ammonia will come as anhydrous. In other words, it's pure ammonia. And like I said, it takes special equipment and great care to use it. But it's very efficient. It's very high nitrogen content. So one tank goes a long way. Okay, I think that's it for today.